Okay, our last speaker is Evaristo Villaseco. He will talk about electronic coherence, the projected nuclear quantum momentum as hidden agent. And first, George.
So last but not least, I'm going to talk to you about electronic coherences and the role of these two guys right here, which are the projected nuclear quantum momentum and reduced quantum momentum or the crunch in driving electronic coherences. This is an introductory description. So this is the outline of my talk. I'm going to start with a introduction to photochemistry and the description of electronic coherences. How do we simulate those processes in an efficient and accurate way through mixed quantum classical methods? And then I'll describe some fundamental aspects of coherences and its importance in some molecular processes. So when we talk about photochemistry, this is the picture we have in our heads. So we have an electronic ground state and a set of excited states, and we excite from the ground to an excited state, and then a wave packet can evolve in time and encounter non-adiabatic coupling regions and basically split or transfer population. So this idea is rooted in the Born-1 expansion, in which the total molecular function is expanded in the eigenstates of this Born-Oppenheimer Hamiltonian. So in essence, all we do is we solve the static eigenvalue problem for the electrons. The set of energies are give us these surfaces or curves, in this case, for the dynamics of these wave packets. And those states actually give us the couplings for the transfer population. So you can think of these non-adiabatic couplings as basically electronic states which are coupled through the nuclear motion. So in this picture, the concept of electronic coherences arises, and they are basically a product of the wave packet components. So you can think of them as basically overlapping space and time of nuclear wave packet components. Now, people often refers to coherences to basically the integrated quantity in nuclear space, and I'll refer to that as spatially integrated coherences. And why do we care about coherences in the first place? So it turns out that they are responsible for a lot of photochemical phenomena. One example is energy transfer in both photosynthetic systems or charge migration problems. They are also very important in quantum information science, think on computers, and they are also very important to be able to achieve tailored chemistry, because it turns out that if you have a long-lived coherence and you recouple the states with a second interaction, think for example of a second laser pulse, you can basically tailor chemistry at will. So that's the idea of coherent control. Now, this idea is very nice, but it turns out that simulating the full quantum dynamics is limited to a very few degrees of freedom. So we have to make approximation. And one set of methods we strive a very good balance between accuracy and efficiency are mixed quantum classical methods. So the idea is quite simple. You have the heavy and slow particles, which are the nuclei, which are going to be treated as classical-like particles. And then the electrons are going to be treated as quantum mechanical objects. So you can think of it as, we have some nuclear trajectories, and along this flow of the trajectories, every trajectory has on top a set of electronic coefficients or an associated time-dependent electronic wave function. And there are two main methods used in the non-adiabatic community, which are NFS dynamics and trajectory surface hopping, which was introduced before. But both of them stem from the same electronic evolution, which stems from this time dependence of consistent field approximation, which says, well, basically, I will approximate the full correlated problem by a product of a time-dependent electronic and nuclear wave functions, and the evolution of one of each of these subsystems is driven by a mean field created by the other subsystem. So it's a mean field approximation in nature. Now, the nuclear force that the trajectories feel is, in a sense, in two different extremes. In NFS dynamics, the trajectory is propagated on a mean field force, given by the gradient of the expectation value of the Born-Oppenheimer Hamiltonian over this instantaneous time-dependent electronic wave function. On the other hand, in trajectory surface hopping, the trajectories evolve on a given adiabatic state, but they can make stochastic hops according to some transition probability that depends, among other factors, in the non-adiabatic coupling vectors. Now, in these two cases, how do we describe electronic coherences? Well, the time evolution of these coherences follows this expression, but I just want to draw your attention to two things here. It depends basically on the delta energy, basically the complex part, and by a term depending on the negative coupling vectors. So, if we have a region of non-adiabatic coupling vectors equal to 0, that quantity just changes by a phase, not in magnitude. So, just as a spoiler, if you have a situation where you have two wave packets that should decohere, but not because of non-adiabatic coupling vectors, just purely because of the different slope of the surfaces, these methods cannot get that. And that's why they have to artificially impose the coherence correction in an ad hoc manner. Now, that you might also ask yourselves, well, what's the right force that the trajectory should feel? Should it be something middle field, should purely adiabatic? And now it's a good moment for me to introduce to you a different way of describing photochemistry that will naturally answer that question. And that's the exact factorization approach. So the exact factorization approach is an exact way of representing the full electronuclear problem or nuclear wave function as a single correlated product of a marginal term. In this case is a time-dependent nuclear wave function, and a conditional term, which is a time-dependent conditional electronic wave function that has parametric dependence on the other subsystem coordinates. Now, if you think about basic probability theory, you know that you can always express a joint probability distribution in terms of marginal and conditional, but this is deeper because it's a probability amplitude. It's a complex object, and there's this factorization can be shown to be unique up to a phase, provided a partial normalization condition. But once you derive your equations of motion for these two subsystems, this is what you get. So this equation might look familiar to you because it's a Schrodinger-like equation with a scalar and a vector potential. Now, the time evolution for the electronic subsystem has a uglier shape. But now I just want to point out that the terms that I'm showing in red are terms that capture the exact electronuclear correlation. And let's take a look at how these terms look like. Just wanted you to pay attention that, for example, these fields that appears on the evolution of chi depend directly on phi, which is the wave function for the electrons. On the other hand, this term, for example, that appears on the evolution of phi depends on chi. So you can see how these two systems are intimately correlated. And in fact, you could think that the nuclear evolution is being driven by an electromagnetic field that's created by the electrons. That's how I like to think about it, even though these are not real space fields in a sense. And another nice thing is that, under this phase transformation that I talked about earlier, this potential actually transform according to standard potentials in electrodynamics. So with this picture, I just want to, we're just going to look at a hypothetical two-level system dynamics in one dimension in the two pictures that I talked about before. Now we're looking at the same process through two different formalism, but we're looking at the same thing, both equally exact. So now let's look at the one picture. We have a ground state and an excited state, a wave packet on the upper state. As time goes by, this will go down the slope, approach another coupling region, and split the density. Now let's look at the same process through the lenses of exact factorization. Now we don't have a nuclear wave packets, we just have a single time-dependent nuclear wave function, which is evolving on a single time-dependent potential energy surface. This is the scalar field I talked about earlier. So as time goes by, this TDPS will develop some features such that it will split the nuclear density. So again, this is the same thing, just looking at it through two different mathematical formalism, but it's the same thing.
So sorry,
Yes.
on the right hand side, the dashed line is just the copy from the left hand side.
Yes.
But it's not.
It is
The green one sort of is dynamical.
Yes.
It goes with the wave packet.
You are right.
So the wave packet is sort of surfing on this
Right.
surface, which also evolves the time.
And that's a really good analogy because you can think of this as your skin on a mountain. This is more like surfing a wave. So your potential is actually evolving in time along yourself. So yeah, I just kept those dashed lines for reference because yeah, it should map that outside of this coupling region. That is a very good point. Yeah. Now, I just want to come back to that question: what's the right force of that is to drive the nuclear motion? And as you can imagine, the exact factorization is going to provide a natural answer because now we have a Hamiltonian evolution for our nuclei, so we can actually point out to a uniquely determined Lorentz type force that should be driving the nuclear subsystem. So to develop mixed quantum classical method, we can treat H as a classical nuclear Hamiltonian, use Hamilton's equation of motion to derive equations for the force and the velocities. So now I can express the force in terms of this field that I mentioned before, and an internuclear force term that appears because of the coupling with the electronic subsystem. So now that we have a nice framework to develop mixed quantum classical scheme, let's do that.
Sorry, where's the very phase? There's somewhere it's hidden inside, right?
It's in the.
It's the vector potential.
Yes.
Well, I mean, it's a different type of variation than the static problem, but yes, the question is, right,
Dynamical phase.
yeah, there's a and then there's various studies which show that, you know, in the dynamical case, right, you don't really have a very phase. I mean,
Yes, it's an art. Yeah.
in the fully dynamical case, there's not, you know, the A dot dr. I mean, no, well, it depends what you call a very phase.
Yeah.
I mean, right, but so curl of A could be non-zero, but it's not necessarily linked to points of singularity.
Yes.
On the surface. I guess that's what we mean.
Yes.
Fitting does work.
Yes. Yeah, I make the distinction between the dynamical
Yeah.
and the very phase, which is kind of an artifact of the representation, right?
Yeah, we thought different, yeah.
So now I'm going to talk about this CTMQC method, and it's funny because Rishi talked about earlier before about CTQMC, so Juan Monte Carlo type. So this stands for coupled trajectory mixed quantum classical method.
But Evaristo, how much time? Because how
Yeah.
much time do we have? Like 5 minutes or something?
Sorry, like 4 minutes.
4 minutes. Yeah, just bear that in mind.
But you start later, then you have a little bit 5 minutes more, then you have around 9 minutes.
Okay.
It's okay.
Then let me see what can I skip. Okay.
Oh, that's good.
That's
That's
just
good.
Please tell us.
I thought I was going to take way shorter.
Tell us.
So I just want to compare side by side because I think that's quite instructive on how this CTMQC is derived from XF with how RMFest is derived from TDSEF. Remember, on the left side is an approximation and correlated product, right side fully correlated product and exact. So the idea is in both methods, I just want to point out also this is exact because this R right here. So that single letter, that parametric dependence makes it exact. So in both cases, you take the classical limit for the nuclear motion. You expand on a basis, adiabatic basis. So the time-dependent electronic pair you expand in a basis. Again, remember that R dependency is carried over to the electronic coefficients. And this actually parametric dependence is going to be key to capture spatially resolved behavior. You make some approximation based on exact studies, but at the end of it, you get here RMFS plus corrections, both in the force and the electronic evolution. And what's important about those corrections is that they couple the trajectories. So now we're going to have a fully coupled trajectory method. And in a sense, we're going to recover like non-local aspects of the quantum dynamics that are really overlooked in this single trajectory picture. So just quickly how this term look like. Well, they depend on this Q, which is the quantum momentum. This is where the non-local effects happen because now for every trajectory alpha, we have a dependence on the full density. So like the trajectories should talk to each other, exchange information. And the F, which is the accumulated force. And well, this CTMQC method has been applied to a variety of systems that capture the coherence, some other things. But what's very interesting is that now, if we compare with Ehrenfest, we have a new mechanism for electronic transitions that's not there before, and it couples all electronic states through this sum K, and it has important consequences, which are going to be important for a description of pairwise nature of coherences and also multi-state interactions. And just quickly, how do you compute Q? Because I'm telling you, like, we have trajectories, how you construct the density. Well, it turns out that for several reasons, I don't want to get into detail, you enforce that condition. You say, okay, over the full ensemble of trajectories, the contribution of that term is 0. And the reason why we do that is because, well, if we are in a region of zero non-negative coupling, we shouldn't expect any population transfer. But I just want to point out that every trajectory individually can have this quantum momentum induced transfer. Is the ensemble that auto-compensate, and that's something very important. And finally, the part that I should have spent more time talking about, let's look at coherences now. Again, as a reminder, these are spatially resolved coherences. Recall that we can map those wave packets with the coefficients on the bond one expansion, or no, sorry, on this expansion of phi through basically, so chi k is chi times c. So, sorry, I don't want to go that fast. The wave packets can be related to the coefficients that represent the time-dependent electronic wave function through the density. So you can always map one to another. And the spatial integrated coherence, which is the time integral, if we want to go to a trajectory-based picture, we represent it like that. All we do is say, okay, our density here is a sum of delta function at the position of the trajectories. Just quickly, we tend to focus on the coherences, but also pre-coherences are very important. This is an example where they see charge migration in silane, which decoheres, but they show revivals of the charge migration driven by electronic coherences after 50 femtoseconds. So what are the challenges for simulations? Electronic coherence is really a state pairwise property, and I will tell you what that means. But the usual decoherence corrections are statewise. By that I mean they impose a correction which depends on active state and non-active states, just a pair of states. And you will quickly see why that's not the right physics. What are the key features that drive the evolution of the coherences, and also if an experiment measures only the spatial integrated coherences, does the spatial dependent matter at all? And the answer is yes. And it turns out that you can actually measure coherences with sub-Armstrong resolution, which is quite impressive. Okay. Let's talk about the pairwise nature of coherences. And for that, we chose a very, very simple model system, one dimension, zero non-negative coupling. We have two parallel states on the top and a non-parallel one, and we start in a coherent superposition of these three states. Now, I can tell you what's going to happen, and you already know. So the two wave packets on top will move together and remain coherent, while they will decohere with the third state. So on one hand, we should find that these two guys remain coherent, they decohere with that third state. Now, let's run the dynamics and see what happens. And here I'm showing the coherence between the parallel states as the magnitude. I have a lot of lines, but I just want to focus on exact, which is in black right here, as we should expect. The magnitude of the overlap doesn't change. CTMQC, which is in blue under here, perfect. Ehrenfest in green under here, just trust me, also maintain constant coherence. And also, this is a surface hopping based method that adds artificially a correction and just dumps it incorrectly. Okay, good for Ehrenfest, the parallel case. Now let's look at the non-parallel case. So non-parallel coherences, magnitude, exact shows the coherence as we should expect. CTMQC also captures the right behavior, at least qualitatively. But Ehrenfest actually tells us that the non-parallel coherences are constant in time. which is not right. And remember at the beginning I said like this is gonna be a problem by the electronic evolution equation that it has, just with a coherence depending on the non-adiabatic coupling. Now, we see that in both cases. On one extreme, the coherence corrected surface hopping dumps the coherences in both cases. NFS does the opposite, everything is constant. And CTMQC gets it right. But how about the spatial resolution? We might be tempted to think, okay, for the coherence between parallel states, NFS work. Is that really the full story? And if we look at the spatial resolution, we see that's not the case. So we see that even though the trajectory average quantities or spatial integrated quantities are constant in time, there's underlying spatial structure. And this is what I'm showing here, 2 times snapshots for this process. We see that the exact case actually the coherence changes, even though if we integrate it integrates to a constant value. CTMQC trajectories maps this behavior, but NFS, every single trajectory is constant. And that's what I was talking about, the spatial structure. Now you can imagine that this trajectory is hiding the wrong spatial structure. So this is gonna be really important if we have a second interaction region. And I'm gonna skip the details, but you can imagine that if NFS is getting the trajectory properties wrong, then the subsequent diagram is gonna be wrong. And just gonna skip this part quickly. And now how about recoherence? Another simple model system where we now see decoherence and recoherence. So let me just focus on the coherences between the non-parallel states here. So we see that Ehrenfest again wrongly maintains non-parallelistic coherences. CTMQC predicted the coherent behavior, but actually all the methods miss the recoherence. And that's an issue. So why are we missing recoherence even with CTMQC? So to understand what's happening, we went and derived an exact trajectory-based picture. So we start from the full quantum equation and then we trajectorize basically by placing delta function on its trajectory. And it turns out that you can derive an exact equation for the time evolution of the magnitude of the coherences. And it depends on these two guys, the reduced and the projected quantum momentum that I'm showing here. So this is for reasons of zero and coupling. And actually in CTMQC, you make a crucial approximation, which is you neglect this term. So at some point in the derivation, you say, well, the gradient of the electronic coefficients is just the gradient of the phase and not the magnitude. So you throw away that term because it turns out it tends to be really small. But by doing that, you're breaking now capturing recoherence, and then you're breaking many more issues, for example, conservation of fundamental physical properties like momentum. But then, yes. So this actually peak is driven by that term, which is neglected, and we call it crunch because of this property, right? We have the quantum momentum, and this term actually crunches down the other, making it a straight line, and it should be the derivative of the wave packet. Sorry, I just took a lot of time. Then we said, okay, what other systems can we try our method on? Well, it turns out that this behavior of parallel surface and non-parallel one is observed in some molecules, for example, 5-ion benzene. And what's very interesting about these systems is that they showed long-lived coherences lasting for like 200 femtoseconds. And that's very important for, as I said, you want to maybe do chemistry that will tailor in your process. So you need a long-lived coherence in time and then recouple the states, use the interference pattern to drive the photo products. So we tried something on the, a linear background coupling model of thiophene, but it turns out that, if we look at the coherence with Ehrenfest, okay, everything remains coherent, but with CTMQC, we see super fast decoherence. So we, yeah, I don't trust much the surfaces, so I think they are not parallel, although they should. And yeah, we are testing also a different model of benzene, which again is not working. I know it upset, but yeah, I just hopefully convince you that these methods are an efficient way of simulating photochemical dynamics and especially electronic coherences. And sorry for taking so long. Yeah.
Do you have any questions?
There are simple ways of introducing decoherence to Ehrenfest. And I'm asking this having in mind, you can always write down an equation of motion for a density matrix, like a master equation or a Liouville equation. And you have something that you could write as a density. There's the CJ, CK, that's something like that. And then, for instance, when you do this for a two-level system, let's say you have two levels, you have a two-level system, and you can always introduce decoherence with what is called, T1 and T2. So one of them is an off-diagonal coupling, the other one is the diagonal coupling, that's then called relaxation. So I was wondering if you could do something like this to introduce some decoherence.
Yes, there's like a huge variety.
I'm sure there is.
Yes, people explore like all sort of methods. Like for example, in NFS there's a method called TAB, which is kind of collapsed into a block of states. Yeah, there are many like so-called ad hoc. I don't want to call them ad hoc, but it's more like they are some underlying physical principle in mind that they're using, but there's a wide variety of
You
methods.
can call it ad hoc, that's fine.
Yeah.
We want to also reverse your question because in some sense the T1 and T2 people talk a lot about that with experiment, right? Or what is the T1? But in some sense, factorization gives you these exact,
exactly.
in principle exact T1.
But then your T1 and T2 are dynamical. They're not just constants.
Right, yes, exactly. But they should be dynamical, I suppose. I mean, maybe in some limits, like in the when you have many degrees of freedom or something, when you're really just getting one pure exponential decay type behavior, then it would be one number.
So if you go back, do you have an equation of motion there somewhere? For one back, where are all there the slide with equations?
For CTM,
No, I think it's
the exact trajectory based ones.
Yeah, where you had.
Sorry.
No, I think now we've gone too far. I forget now, but it was sort of towards the end where you then have one term that is neglected.
Yes, sorry.
You go forward.
Yes,
sorry,
it's not take a long time.
No, that's fine. I think it was maybe the next one.
Yeah, the next one.
Yeah. This one here. So where you says reduced quantum momentum. It's that, I don't know what kind of symbol that is. There's a sigma, there's a Q, and there's sort of a curly sigma. Is that sort of
So we call the crunch.
the crunch? Is that these generalized T1 and T2? No, not really.
It's exactly that.
Yes,
I mean, I think it would be really, I think that plus the thing is, it's also non-linear, right? T1, the concept of T1, T2 is kind of thinking of like if we look at our equation of motion for this, like you can see on the right-hand side, actually my eyes are terrible, but that there's also you know what I mean? Like, sorry, if it was simple like T1, T2, you'd have d1 dt of something equals something times T1.
Yeah.
Yeah, but look at the thing, it's a nonlinear set of equations, right? So you've got dt of something equals something times c squared sum on n.
So it's not that.
Yeah.
Yes.
You have to somehow linearize the thing if that's possible.
Right, then maybe but I think it's an interesting question. I think you haven't raised. I mean, I think one could try to, and maybe in some physical circumstances, right? I have to think, right. The conditions where you do expect like kind of a exponential relaxation, then one should be able to linearize
I'll
this.
give you some insight.
Yeah,
That's a very good point.
friction, like electronic friction.
Well,
Right?
friction, anticipation, or whatever it is.
I've also to say that this actually is when non-erratic couplings are zero. If we want to write the full equation, it's monstrously ugly and low.
It's not, yeah, there's not an additive term that depends on the non-negative.